Hi, my name is Dorota. I'm working for MIT, and Satya Ghosh is my PI. So I've been working with Airplane for like a couple of years, and yeah, I will be teaching Introduction to Container today, and Pierre will be helping me, and he will be also like answering all the questions you might have. So
And can Pierre, yeah.
Yeah. Hi, folks. My name is Per. I work with Jean-Baptiste Pauline at McGill University. And as Dorota mentioned, I'm going to be the person in the background today. So whenever you have questions, and ask them in the chat or maybe the Etherpad, and I try to address them ASAP, basically.
So just a couple of things, like, you can go, so the idea is that, you can feel free to ask any question to the Zoom chat window. And I'm sure like Per and others will be like reading this question. One thing that is not very convenient with Zoom is to copy paste the comments. So pasting and like everything will be in the Etherpad. And this is also like already like, so I don't know how many people already like installed Docker. I guess I asked here and some people already answered, but if you do have Docker and you would like to follow the example together with me, one thing that you can do right now is just follow this 2 points, just mostly like pull one of the image and just to have ready any T1 image that you might have and you might let you use for as an example. On the right, you can like put your name. So when you are here, you can put your name here so we can see. I mean, you don't have to, but just you might wanna. Yeah, so, one of the things is that, oh, sorry, I wanted to do, no. Okay, so one of the things is that, I really cannot see you. So in this, like, it's really like harder to teach people like not seeing their faces. So I would just like to like, really emphasize that you should interrupt. Either you can ask question, in the chat windows and someone will ask, someone will answer, or you can just interrupt me. And also like other Planium instructors can also like interrupt me if they notice that people are confused. So please don't hesitate to ask question either like online, either in chat or just showing up. Sorry, I'm getting there. Sorry. Okay, play. How can I remove you? Oh, okay. So the first lecture, like first workshop this afternoon, will be about container technologies, and that will be like really like short introduction to the container technology. And as I said, I'm part of McGarry Institute that is at MIT. So I will start from a short motivation, and I will be talking about like scientific workflow and reproducibility. So the way how I usually like think about scientific workflows, and that's actually like been true for like, already hundreds of years when people are like creating, making experiments and doing research, is that, like simple scientific workflows has like different parts. So first you usually do some experiment using like simple or more complex measurement tools. You have some theories or equation that you want to apply to data that you get from experiment. And then you have like scientific computation, and then you publish the results. And the idea of reproducibility, I just want to also like emphasize that is also not new. So basically for like hundreds of years, people knew that in order to fully accept the claims from someone's research, you have to be able to reproduce the results. And by reproducing the results means that, one, you are able to prepare the same experiment based on the description that someone gave you. And you are also like, you are able to use apply the theory or equation to the data from the experiment and get the same output. So that idea is pretty old, but many things has changed. So first of all, like we have much more complex experiment and measurements. And because we have much more complex measurements and we are able to ask more complex questions, but we also require more complex analysis and algorithms. And having this more complex analysis and more data, we actually ended up having like bigger group of scientists and software developers that are working on this. And we actually often required much more, rely much heavier on the computers. Yet for some reason, like the only thing that hasn't been changed is usually the way how we report the results. So we still like heavily relied on the results published on like papers or PDFs that do not necessarily contain all the information required to reproduce fully the research. And in this talk, and also like in the next talk, we'll be mostly focusing on the part that is related mostly to the analysis part. So basically, by analysis part, I mean that you have data from the experiment, and you are applying the software and analysis to this data. So we are not talking about the way how you make the experiment, but what you are doing with data after this. So as you know that data is became much larger and also like more heterogeneous, and the analysis became much more complex and also much more heterogeneous, and requires also a complicated, more complex hardware. And unfortunately, as we realized some time ago, the results are not always easy to repeat because it depends on many different things. So what affects your analysis? So the four things that we often think about is that definitely it depends on the version of the script or analysis you have, the version of data you have, but also like on computational environment. That means operating system, compilers, language version of languages you are running, etc., and also on the hardware. And what can we do about this? So first part, version of the script, it can be relatively easy controlled by the version control systems. And one of the most well-known example of the software is Git. And together with a web server that is known as GitHub. We will not be focusing on Git, but later today we actually will be focusing on the second part, that is like how we can deal with the data, how we can control the data in a way that we are able to reproduce our research. And for this, we can control using data. And the second class today will be focusing on data. As we go to hardware, it's actually something that we are hardly ever control, because we might have to change this hardware pretty often. We might have to be like switching between your personal computers, your servers at work. You might be working with colleagues that have different computers, etc. But there's also like these things between that is called computational environment. And for this, we do have some limited control. So, we don't necessarily have to control what is the original operating system on your colleague's machine, but there's a way to run something what is called like virtual machines or container in order to reproduce the same computational environment. And this is the topic of today's session. Okay, so containers. So the definition of the container is that it's standardized unit of software that can be run anywhere. And in maybe like slightly less abstract way is like, if you ask question, what do they provide, is that first of all, it provides you standard method of creating and sharing the computational environment. It also like isolate the computational environment from your local environment, and it can be run in theory at least in many different platforms. And then lastly, it's not so easy fortunately, it's not easy to change permanently, unintentionally at least. So the second question is, why do we need containers? So as we are part of repronym training, we are, of course, we are like focusing on reproducibility as a long-term goal. So basically, as we said, like each project depends on complex software, that is like operating system, software, etc. And having the container, we can always encapsulate the environment. So later, either you or other people later can recreate exactly the same environment. So this is very helpful for science reproducibility, but this is long-term goal. But I also like want to focus that, you know, you could also have like short-term goals that might be also appealing. So first of all, like collaboration with your colleagues. I'm sure that many of you are working with colleagues, and it's not always easy to work on the same software and in the same project, because you might have some issues with reproducing exactly what your colleague is doing. And containers might be like perfect solution for you, because you can share your code using, for example, Git. You can share your data using, for example, Data Lab, but you can also use containers to share your environment. As we mentioned before, like you might also like, you on your own might be forced to change hardware more often than you want. And because basically often personal laptop might not be enough, and you must run the same analysis on various different hardware. And containers, again, is a perfect solution because it can encapsulate the environment and run on different machines. And also, like, what is good that you are able, having container, you are able to run, you know, experiment, run different version of software, try which one works best for you, and, you know, just you don't have to worry that you will like break your original environment. Okay, so and the last one also, like, you know, for people, especially for people who don't like installing things, there are many existing environments. So, you know, installation is not always easy, especially because like neuroimaging software is rather like complex, environment. Like it's like the software comes from many different labs, varied in using many different languages, and having installed them all is not always easy. But basically, there are many existing containers that they might be just ready to use. Okay, so now we will like compare a few tools that are used by us. So in a way, like you often like hear about containers, but also you might heard about virtual machines. So by virtual machine, people often like think, like VirtualBox and AWS, Google Computer Engine, and etc. That but when we say containers, we often means about software like Docker and Singularity. We don't really have time to talk too much about like differences, but just one thing that I want to say, that the main idea is the same. It's just to isolate the computing environment and regenerate and share the same computing environments with others. But basically, containers are a kind of newer technology and are much lighter and faster to start up. And that's the reason why they became much more popular recently. So we will be focusing on Docker and Singularity, and all the example will be on using Docker, but because in the future you might have to use Singularity, I will also like say a few words about Singularity. So basically, Docker is a leading software container platform. It's an open source. It runs on like Linux, Mac OS, and Windows. With Windows, it slightly depends on the version of the Windows. So for some Windows, you can install Docker directly. For others, you have to install virtual machine first. The only problem is that that the user have root privileges inside the container, and that might lead to serious issues. So often, like, you will not find Docker installed on your local high performance computing center because of this issue. So this is actually the main motivation behind the Singularity, that basically is a newer software that is basically provide a solution to created for scientific application that can be run in high performance computing centers that you might have access. Basically, the user inside the container is the same as outside, so this doesn't lead to any issues related to security. The only thing is that Singularity for Windows and OS X has limited support, and you might have to install virtual machine first and the Singularity inside the virtual machine. Okay, so maybe if there's any question, you can let me know, or I will just have like short introduction. What does it mean to use container? If there's any question that I don't see the chat, so you must.
I'm not seeing any questions at the moment.
Okay, so I'm going. Okay, so what does it mean to use container? So as we were saying, this is like containers is a piece of software that is using, it's recreating new kind of computational environment, but it's using obviously the same hardware as your local system. So basically, like, you can imagine that you are creating an extra like computational environment and user space within your like laptop or computer. And below, I will be always like the slide has also like the commands for both Docker and Singularity if you want to run this in the future. So and what is cool about this, you can actually have like multiple different containers within your laptop that they will be like all sharing the same hardware, but they will have completely independent user spaces and libraries. And we can concentrate on like one specific one, the specific container, and what does it mean to work within. So basically, let's later today we'll be running the example of container that has FSL, and we will be running the BET, so FSL brain extraction tool. So so basically, like you will have the container that we have like new software installed. You don't have to have this software installed on your own computer, but you will have inside the container. But what you will see, like that the kind of default way how you run at least Docker is that there is no connection between your laptop and the container. So you might have an issue with like using the software to run it on the data that you have on your local machine. But every like software container technology allows you to have some create some connection between your container and your local machine. And one of this type of this connection is like binding the local directories. So you can always like, so you remember like the container is kind of like an independent environment, but you can specify connection. With Docker, you can ask which directories you want to share with your container, and if they should be like read only, write only, etc. For Singularity, you might have different default settings. So for example, like as a default, you might have some of the directories bound as default, for example, your home directory. But for Docker, as a default, you don't have anything. So you have to bound everything. So it's in a way, it's kind of more secure because you will not be removing anything by mistake. So as I said, you can there's many ways of binding these directories. It can be bound like in a read-only mode, but it can also be bound with writing options. And so this was kind of short images to present. And now I think it would be nice if we can run this like simple examples on your own laptops, and it will be like live coding. But I just want to have an idea how many people actually have so I see like on this Etherpad that some people install Docker, so that's really nice. So for people who are late, so I ask people to pull this image. So I will be running. So I already have this image, but so basically nothing will happen when I pull it. But yeah, you should be, if you don't have, you should pull it now in order to follow the example that I'm running right now. So okay, so we can so for people who do have Docker, and if you have if you know that we don't have time to install from scratch right now, but if you know that you installed but you have some minor issues, you can just write on chat your questions.
I'm just going to throw in, we'll also be available for office hours and things, tomorrow. And again, we're always findable. If you want to do this later, and are having issues, let us know. We will somehow help you.
But for people who do have container, I strongly, invite you to join me. I will be doing this relatively slow, so you can follow me. So one thing that you in order to check if you do have this this image that I was asking for, you can type Docker images. And once you type Docker images, you will have, and I will explain later a bit more what exactly does it mean to have images, but you will have a kind of container software available on your laptop. So you see one of this is like FSL image or FSL. So yeah, so this is the image that we will be using. So so as I said, at the very in the presentation, there are different ways of interactive with your container. So one way is to interact, to run the container interactively. And for this, by the way, is it big enough, Dave, or someone, can you confirm?
It's working for me. If anyone has issues, let us know, but it looks good to me.
Yeah, so we can go to this container and work interactively inside the container. And for this, we'll be using the IT flag. And I will always use the command. I will not explain all the flags that you might want to use it, but RM, basically --rm means that we'll be removing the container after we are done. So yeah, so we'll be doing, and at the end there's the name of the container. So if you downloaded my container, it should be like this. So one thing, I have two terminals. So on the right, I will be always using this. Will be always my computer, and here I will be running the container. So you see that, in order to see that you are actually in the container, you see that, there's a different prompt. And, you can see that, you can, for example, like type pwd to change where you are and check the content of your directory and maybe even the home directory. And you will see that you are clearly not on your own laptop, but you are within the containers. You can also check that you indeed have the FSL bat installed. Basically, as I mentioned at the very beginning, as default, you don't have any connection between your laptop and the container. So basically, as you see in the home, there's nothing. So even though we do have the software, we're not able to use it on any data that we might have on our local machine. So let me leave this for now. And
quick question, Dorota.
Yeah.
What operating system are we in there?
So in the container, we were in the Linux, GNU Linux. I believe that was based on Debian. It is defined the way what exactly the distribution is. It's defined the way how we create the containers, images, and we'll be talking about this later. So.
Okay, thanks.
So again, hopefully everyone who is trying to follow was able to do it. And now, so, I also like mentioned in Etherpad that you will, in order to run the example, you will need at least one image as an input to the embed. So I'm in the tmp directory. And the fix I have a Docker file you can ignore for now. You can even actually remove this. And you will see that I have my image within the data directory. And now I'll try to run the bet for the bet software using my input directory. So now let's do it like once again. But in order to see my image, to see my T1 image, we will create a binding between my Docker and the local machine. So as we said, like during the presentation, Docker has an option to do it, and you are basically saying -v your current directory, and for this you can use just $sign pwd if you are at least on Linux. Data column, and you are using the directory within the container. The directory within the container doesn't have to exist, so you can just create your own name, and I will be using data. And again, you can use rm, and we'll be using the same file, the same image.
Is that --it or !it on that?
That should be single. Thank you. Yeah. So now again, you see that you have different prompts. You are already inside the container, and now you can see that remember like before. Before when we were checking the content, we didn't have any data. But right now, because I created this mounting point, you can see that within the container, you have the data. And you can even see that actually it does contain the file that I had on my laptop. Yeah. So remember on my right, I'm always on my local machine. So you see that this is the same content as I have on my laptop. So now I'm actually able to run the bed. Yeah. So right now I can run bed and provide the name of the file. The only issue is that if I provide the output, and let's see, it will take just a couple of seconds. Okay, so it completed. So maybe for those people who don't know, if we ask for bed help, it usually like gives like bed input as a like input file and output just using the prefix for your output. So if we check what was created, you will see that bed indeed gave me an output. But the only problem is that it's only on the container. Yeah. So I don't see this file anywhere, either in data or in the output. Because we actually like the only place that we created the connection between container and local machine was the data. So I will not be able to see inside. I will not be outside the container. I will not be able to see the output. So basically, the way to do it would be in order like to propagate this to the output, I have to add another binding. So also like I can slightly modify the bindings for data. So I told you, and I can use it now as example, that you can also like protect your data, especially for like your raw data, like input data. You can protect this using read only. So there's no way that by mistake you will remove your data. But for output, obviously we want like be able to write inside. So you see that on my laptop here, I have data and output. So this was already bound to the container, and now I will be binding the other directory. And I will be also calling this output inside the container. Why is wrong? Because you have to actually repeat the -v flag. Okay, and I'm again in the container, and I can check the content of my list all the directories, and you see that there's data and there's output. Remember that you can check this, and because it's now read only, I should not be able to modify this. Let's see, hopefully. You see that now, because I restricted this to read only, I'm not able to modify anything in this directory. Okay, so now let's run the example again, but this time we'll be using the data, and we will be in the output, we'll be using output and beds out. And again, it will take like a couple of seconds. And I will check the output. And so here, remember, we are in the container, we have output, and let's check. And here on the right, I'm in my local machine. And you see the output, it's there because I created this like kind of like double bounding. So like just to refer to my presentation, we are in this situation. Yeah, we bound the data and we bound the output. So right now, everything what we are doing in the container and we save in the output will be later visible in our like local machine. So this is basically like the small example how to run things within container. You can also like check that even if I exit the container in my local machine, my output is still there. That was an example how to interact with container using this IT interactive mode. The other way of doing this, we can also like do exactly the same thing, but instead of just having this interactive mode, we could just run specific command using this container. And in this example would be like bed. And here we're providing input as it would be in the container. So data my T1B, T1W and output. And I will just call it new output just to see that it's created second time. So here we are not going inside the container, but we're using the software that is installed in the container to run specific command without going to interactive mode. And we can check that again, the output in my local machine. So you see like the second output was created. So this is like the simple like interaction. So if anyone tried to run with me and had some issue, you can just unmute yourself and actually ask a question, or you can ask on the chat window. If there's any question? So okay, so in this situation, that remember, like I ask you to pull the image from my Docker Hub, and I ask you to actually at the very beginning to list Docker images. So you had like a list of images, and later we were like running container that were based on these images to run the software that is installed. So you already know how to interact with the container, but let's talk now more about the image itself. So what is an image? So this is basically an immutable file that contains all the source code, libraries, and dependencies and files. And can be treated, and this image basically is the thing that when you ask for pull, you basically download it from the Docker Hub, and that was already prepared by me. And this is called image also because it can be in a way treated as a snapshot that represents environment and other software at a very specific point in time. So basically, I created this image yesterday, and that basically was the version of FSL that I installed yesterday. For Docker specific, the actually image contains multiple layers that can be reused by various images. That might be nice if you are having like a lot of Docker images, and they might be big. So the way that we might be reusing the layers might be also like actually pretty convenient. So in order to run the container, the image is needed. So that was the reason why we were running the example for like FSL container, and at the beginning you had to have the image to run this. And several containers can use the same image. They can use like over and over. So you saw that I was running the same image over and over, but I could also like run at the same time multiple containers based on the same image. So how we can think about it? So yeah, so if we have like one specific image, we can create multiple containers and they will be all the same. So that's the nice thing. That's why you can share. That's why other people can reproduce what you've been doing, because you know that if you have specific image, you will have exactly the same container. You can change the containers later, but that's fine, because while you are changing these containers, you can be even able to save the changed version of the container. But you can always come back to the image and create another container that will be pink. So how do I get the image? So one way of getting image was you already tried. So basically get from public repository from Docker Hub that's the way how you get my the one that I prepared yesterday. You can receive from collaborators, but you can also build your own from something that is called Dockerify. So okay, so it's another like animal that is called Dockerify, and how do we get one? So basically, Dockerify is a text file that contains all the instruction that is needed to define and build specific image, Docker image. And unfortunately, you have to write your own. That's the part that you have to specify. You really have to specify what you wanna install inside your image. It sometimes might be easy. Like for example, here is an example. Like, and that was I mentioned. I'm sorry, before to answer Dave's comment that as always you start from a specific base Docker. In this specific case, it was Ubuntu, but it can be Debian or NeuroDebian, and you run some you install software in a similar way as you would be doing in Ubuntu. But obviously, it might be much more complicated. So this is like one of the version with more complicated for FSL. And you can write this on your own, but there is also like a software that is called NeuroDocker that actually can help you with this. So so what is NeuroDocker? So this is basically the software that allows you to simplifies the writing Docker files and Singularity files. So basically, it helps you to write these instruction files that is used later to create the images. And the nice thing is also that it simplifies and it also incorporates the best practice for installing software. And maybe it's also that the container, it doesn't get bigger than it has to be. And it supports popular neuroimaging software like AFNI, FSL, FreeServer, etc., as well as like general purpose, like for example, Python. It can be also used together with ReproZip to minify existing Docker images, because for people who already use Docker images, they know that they might be sometimes pretty big. And yeah, so basically the same code that the code that I showed you on previous slide that was rather long. It's basically you can get by this command using NeuroDocker. Basically, you are like specifying that where is the distribution that you want to get the FSL, and we're using NeuroDebian. We're using apt as package manager for Debian, and we're just asking to install FSL and adding some extra entry point. You can go to NeuroDebian website, not NeuroDebian, I'm sorry, NeuroDocker website to see examples. No, go away. And actually that, the last small exercise will be, it's actually just to run, to create our own image, image that we'll be using in the next section of this training. How much time I have? Oh, okay, I have like 10 more minutes, so that should be good. So okay, so basically, again, if you have Docker, you are welcome to join me and ask questions if something doesn't work. But basically, we'll be trying to create an image that has Nylon and Matplotlib inside. So again, like I show you that we like suggest to use NeuroDocker to create a Docker file, and that supports many different software. And one of the software is Conda. So Miniconda, that can be for people who never use Miniconda, that actually can be used to create new environment, but also like just to install additional packages for Python. We not go into details, but basically by saying that we support Miniconda, we mean that we support the Python and various libraries. So the way how we will like run this this command today is that we will be using actually like, so the way how to get the I'm sorry, a NeuroDocker, we can install NeuroDocker on your laptop, but you can also run a NeuroDocker container in order to generate the files, the Docker files. And that's how I will be doing this. So I will be cheat a bit, but just to, because we're running out of time. But so yeah, so basically you should be you should already like recognize this part of command. So we are using Docker run and specific container. So in this we are using container that actually use NeuroDocker, and the command to generate the Docker file is generate Docker. And if you see the example on the website, you will see that what things you have to specify if you want to create Docker with Python. So as I said before, for every single one, you have to specify some base image. In this case, we'll be using Debian. The package manager for Debian is apt-get. And there is like, we'll be using Miniconda in order to install Python. So here you have like example that you install Python 3.6 and NumPy, pandas, and traits. And pretty much the only things that we'll be changing here is that we'll be using Python 3.8, and we'll be using Nylon and Matplotlib because this is the software that you will need for your session, for your next session. So maybe I will post this. I will post this command here. It's in line 9. So for anyone who might not, who might be slightly too fast, I just post on the Etherpad the command that you can just copy paste. In your case, it might be it takes slightly longer because you might have to pull the Eponym NeuroDocker container, but it's pretty small, so it will be fast. Okay, so we basically generate the Docker file, and we can check now the content on Docker file. So yeah, so this is how the Docker file, that as I said before, this is kind of the text file that contains all the instructions. So this is how it looks like. You can write this everything by hand, or you can just use NeuroDocker to generate this. So for now, we have a Docker file. In order to build the container itself, we'll be using Docker build to create image based on this Docker file. So if you also want to follow this, and you'll be using this container for the next session, you can run Docker build OT. And we use the -d option to call it this. So this is name of my image, and at the end is dot. I will also copy paste this here. And you see now it's taking basically the instruction from Dockerfile, and it's creating the image. So one thing that for you, it might be much slower. I'm cheating a bit because I remember I told you that Docker image contains different layers and they might be reused. So I do have many of these layers. So for many of these layers, I'm not, I think, oh, actually I have to run. Okay, so maybe I changed something. So, so it will take some time. So if you are running this, just let it be let it run in background. It will take a couple of minutes before it will finish. But you see that you are actually like, that's the process of building the image. So if you have any question, you can ask me now, or if not, I have like 2 more slides. And on the slides that we also like make available for you, I have exactly the solution for this task. So again, oh, I'm sorry. The first command is used to create Dockerfile, and the second command is that it takes a Dockerfile and the way, because it's used Dockerfile name as a default, so I don't have to specify it, and use this this file to create a new image that will be called Niger. So one more thing about the images and Dockerfile or Singularity file. It's kind of like, again, it's kind of recipe. It's a text file that contains all the instructions. So you can treat it as a recipe. But one thing about this that, you know, recipe might be the same, but if I ask for Python today and I ask for, oh, I should have changed already the years. If I ask for Python in 2020 and I ask for Python 2021, I might actually have different Python because, you know, the default version might be different. So, so you have to be aware that, you know, having one specific image, you always recreate the same container. But having one specific Docker file, it doesn't ensure to recreate the same image. And actually, it might have happened exactly the things on my laptop that, you know, the things that I created yesterday is slightly different than today. So having different image will, you know, will lead to slightly different containers. So this is something that you have to be aware. And there's also a way to, you know, to be very specific, to use something, what is provided by NeuroDebian freeze in NeuroDocker. And that basically allows you to ensure that the Docker file is enough specific that every single day we recreate the same image, and those we recreate the same exact container. And yeah, thank you, that's it. So I hope for people who are running the examples, you know, it will still take a couple minutes to run this. But yeah, I will stop sharing the screen and, oh no, I will not be leaving. No. Stop sharing the screen, okay. And yeah, if you have any question, please just unmute yourself.
Actually, for the fun of it, if there's questions, that's great. If there are folks out there who actually did try to play along and who succeeded at play along, can you raise your hand or something just so we can get a sense of, actually, if you tried at all, raise your hand so we see, just to tell who was, you know, trying versus enjoying the lovely presentation. Okay, there's a handful of hands that documented attempts. Excellent.
Cool.
And of you folks who attempted, yeah, but the thumbs up, you know, to say that you actually succeeded. It's a test of your Zoom skills after this year to see if you can find a thumbs up. You know, just that's great. I see only one thumbs up. Okay, two. A couple people made it through that. Okay. when we do this live, we have these little sticky notes, and we get people running around the room helping folks. And so our version of help, now is going to be discussion afterwards, or office hours tomorrow, or various other ways to get help to you. But anyway, we wanted to at least augment the instructions about containers with a little bit of practical stuff, so that you have a chance in heck of trying to apply that to your real world problems, which are always a little bit harder than the ones we're showing, but at least we got you started. And NeuroDocker is a great lifesaver in getting your containers to a great starting point. And then you can always add additional things to it as your complexity increases.
And if you didn't succeed, like, you also should, just let us know so we can help, or, at least comment where you might have an issue. So yeah. Or if you have any other question, please unmute yourself. I didn't read the question right now, so hopefully if there was any question on this chat, it was answered.
Okay, and so that Etherpad will still be there, and maybe for managing time, we will move along to the next section with Adina and Jarek. So thank you, Dorota.